Hello, everybody. And now I'm going to explain a bit of how to use the subroutines, because we're going to need to use some subroutines for the next tutorial. As I said before, the idea is that before the end of today, you submit a job that will run overnight in Archer, so we need to move on, basically. So we're going to talk about how the main subroutines work, and go give you some examples in Fortran and some examples in C. So when you run the case, as I said before, everything that is in the SRC folder will be compiled and linked to the installation that you have CodeSet. That means that whatever you change and put in the SRC file is gonna have precedence over whatever it was for installation. That means that it's not only the user subroutines, but any part of the code, any subroutine that you put there will be the one that is valid. So that allows you to actually change more than just the user subroutines when you want to test something, for example. As I said before, there's a reference directory and an examples directory. They can be either copied into your case when it's created, or you can find them in the installation directory, or you can access it via the subroutine editor that I'm going to show you in a minute. Needless to say, the user guide and the help and the theory manual have a lot more information on the subroutines, as well as the Doxygen documentation, which I'll show you at the end. So some of the basic subroutines, the main one is CS user parameters. There's two versions. There's one C version and a Fortran version. The idea is that we're slowly moving towards C. So for ease of use, we're keeping the Fortran for now, but that will eventually disappear. The boundary conditions, as the name is self-explanatory. Here's where you need to define the boundary conditions. You can't run a case without boundary conditions set up beforehand, so it's very much necessary. And one thing to remember is that the periodicity, if you have periodic boundary conditions in which you have one thing coming from one side and being recycled into the other, like when we just did with the tube bundles, that's not a boundary condition. So it's not set to CS boundary condition. What really happening is that those phases become internal phases. And I'll go through that later. Another very useful subroutine is user physical properties, where you can define things like pro, speed, etc., as a variation of temperature or the variable that you want to use. CS user initialization, again, self-explanatory. CS user extra operation is a very useful tool for doing anything that you want at each test step. So it's the last thing that happens during an iteration, and you get access to do pretty much anything that you want. You can compute budgets, you can extract profiles, you can compute things like friction coefficients or forces in surfaces or anything. There's a lot of examples there of how to do things that can be done either during the resolution or at the end, the last time. CS user post-process is also very useful to create different parts or add variables to your post-process output. So for example, you can add a variable based on, for example, an example of how to compute the turbulent kinetic energy in a random stress model, for example, things like that. And the CS user system, which is the one that we're going to be using today, which is basically for any type of any equation that is being solved, you can add additional source type. So you just in the previous tutorial you added a force as the graphical interface as a source term in the momentum equation, to drive the flow. You can do that, but not only as a constant, but as a function of anything that you want. So in general, all the subroutines start like this. You will see when you open a file, you have the API license, and then you have a description of what the subroutine is called and what it does, all commented. Then it tells you what the arguments are, the variables that come in and out, and then you start the subroutine with the keyword subroutine. So you have module files that are used to from the main part of the code, but you can also use your user module files. And then you have your arguments. So you have your arguments that come as part of the subroutines and the local variable. By default, all the files of the subroutines in Fortran CodeSet have implicit none. So everything has to be defined explicitly. That helps avoiding many problems, but it means that you have to define everything every time you want it. So then you define the type as integer, double precision, or an array, a pointer. Things to take into account is that Saturn is always double precision. So you should declare your variable double precision to be coherent with the rest of the code. You'll see a lot of variables that have 6 letters. This comes from the legacy of Fortran 77, when you could only have 7 characters. So you'll see that everything that starts with an I used to be an integer. That would help you finding out what it is. And as I said before, anything that you put in the SRC folder will be compiled. So if you have your own function to do something and you want to include it somewhere in the code, you can do it by just putting it in there. You don't have to modify any of the scripts. CodeSet to include files that you. If you are going to put a subroutine that wants to read a file, for example, or you have some sort of data that you need to access, put it in the data directory, and it will be copied automatically to the execution directory, wherever that may be, depending on the installation on the machine, and it will eventually be copied to your results directory when it's finished. So if you're going to read an index profile, don't put it in SRC, just put it in data, and you don't have to give the path to the subroutine. It will be found when it's executed. One thing that is very useful is that you can use the command compile to check the compilation of the subroutines before you launch calculation. This is very useful because sometimes you send a job to a queuing system like in Archer. You see that in the tutorial, and it might take a while to start running. There's no space, and you have to wait until someone else is finished, and then it starts in the middle of that, and then you have compilation error, and you've lost your place in the queue. So it's a very good practice to compile everything before you run, to make sure that you don't have any compilation errors. So some of the main variables that are useful to know. NDIM is the number of dimensions, which is 3. But it's used to dimension all the arrays. N cell and N select are the number of cells. N cell is the number of cells in each rank of the data, and N select is the total number of cells, including the ghost cells. And I'll go through what the ghost cell is in a minute. NFAG and NFABO are the number of faces, interior faces, and the number of boundary faces. you see this box loading in the code, that's because French box is the boundary. So internal faces and boundary faces are treated completely different in the code because an internal face has two cell centers, part of the connectivity, whereas boundary face has only one center. So it means that all the arrays that store information about this are different sizes, so they are completely separate. And varies the number of variables, so it depends on how you set up your case, how many scalars you have, what sort of physics you're solving, or what turbulent model you're using, etc. FML is the number of families, which is basically the type of boundaries. So when you think about a boundary face in the code, it means each one of the faces that make up a region, that region being the inlet or the outlet. So each region has a subdivision of number of faces, and the number of families is the number of types of zones. Number of properties is the references by each one of these families is PRF. Number of scalars is also very useful when you're doing things like temperature or concentration. You need to know which scalar is the one that you're dealing with. And there's some geometrical arrays that are very useful to know. Like XYZ center is the cell center coordinates, whereas CFD is the center of the coordinates of the center of gravity of the face, and the BO is the boundary face. Surfac is the vector normal to the face, internal face. The length of this vector is the area of the face, and so BO is the same but for a boundary face. Volume is the volume of each cell. As said before, we have finite volumes discretization in CodeSet, so that's very, very important. Everything is volume weighted. And these two last arrays are the connectivity between the faces and the cells. Because this is an unstructured code, there's no connectivity like north, east, south, or west, or I plus one, or J plus one, or K plus one. The only connectivity existing is between a face and a cell center. So a cell can have any number of faces, but an internal face will only have two cell centers, and a boundary face will only have one cell center. So that's how the connectivity is built. So when you discretize your equations, you sum over the faces of the cell. CodeSet has its own API for accessing the different variables. It's what it's called field in CodeSet. A field is more the order of spatial discretization is second order. And that's it. There's no more. It can be order, second order in time as well. But that's it. In CodeSet, a field is more than just a variable. So a variable will have certain properties that are more than just the value at the cell center of the temperature, or the pressure, or the velocity. It has things like what's the maximum number of iterations that it's used to solve the linear solver for that particular variable, or what coefficients do you have for the boundary conditions, or what sort of gradient reconstruction you're using for that particular variable. So all those extra information that is needed are stored in the field. So you can access a field, and you can access much more than just the value of that variable in the cell center. And that's where we have their own API. And it works by calling different functions that allow you to get things from that field. So in this example, this function field get val s means get the value of a scalar. S is for a scalar and V for a vector. And what you're gonna do is put this pointer to access the value of the cell. You can see this. So in this example, you get the field index, which is this first part. I bar FL is the field for the variable, and IPA is the index for the pressure. And this function searches for this index and returns this array where the pressure value is stored. Okay, so for any given cell IEL, the value of the pressure is given by this. Similarly, for a vector, in this case the velocity, you will use this function to get the 3 components of the velocity, 1, 2, 3. Okay. You can get also things like everything that is stored in the cell center, you can get it. Like you have variable CP, for example, or variable density, or variable or tubular kinetic energy. So all of these indexes for the variables are listed in the oxygen documentation, and they're explained through the examples as well. There's a big list, and you can find whatever you need there. I'll show you later. And in C, it's slightly different, but it's the same concept. You have a field, and then you get the field name, and then you, from that field, you extract the value of the cell. Okay. And again, these names are also defined or can be found in one thing to note is that indexes in C begin at 0 and Fortran begin at 1. So just remember, your loops in Fortran start from 1 to L, whereas in C will start from 0 to L minus 1. And the cell ID of C is going to be the 1 Fortran minus 1. So I'll show you an example of the oxygen segmentation in a minute when we finish this. So you can see what I'm talking about. And so, for example, if you wanted to change the density given by this formula, you will go into CS user physical properties, subroutine, and declare your pointers. So in this case, will be a pointer for the temperature and a pointer for the density. And this index, I bar T, is the index for the variable temperature, and is found by going into the scalar array and find the scalar for the temperature. Okay. These are just numbers, indexes, but they vary depending on your setup. So you don't need to find out which number it is. You can just do it like this. Then you get your value using the function again, field get val. You get your value for the temperature and you get your value for the density. Now you have these two arrays where you can modify the values. You can read them and modify them. And in this case, we have these ABC variables declared locally. And what you will do is do a loop on all the cells. So the IEL will be a counter that goes from 1 to the number of cells. This would be just your temperature value given by this for this particular cell. And this density will be given by this representation of the formula above. So your constants times your temperature times plus B plus C. Okay. Another example here is how to initialize the temperature at the beginning of the calculation. So in this case, you have a test here that this I switch is a number that will tell you whether you're starting calculation from scratch or restarting from a previous calculation. Okay? So in this case, we're setting it only to change the temperature when we're not restarting regulation. Make sure that when you restart, you don't reset your temperature values. And we do the same. We call the function for the scalar, and that scalar is set to 25. And here's another example of how to do the same thing for the velocity, but in this case it would be vector, and in this case you have something that changes in time. So this TT counts is the current time in seconds. Now, a little bit more on the boundary conditions. As I said before, you need to assign for each phase, not only the region, but for each phase, it needs to be assigned the value. So you need to assign what type of phase boundary condition is. Could be a Dirichlet, it could be a flux condition, and depending on what type is it, you can define the value. Okay. So you have these types predefined, which are inlet, walls, rough walls, symmetry, outlet, and this one is generic, undefined. So when you set I type FB to one of these predefined, there are some arrays that are filled for you. If you use undefined, then you need to set all the boundary conditions for all variables for all the phases. So depending on what type of boundary condition, you would need to set the actual value. So if, for example, you say that a phase is symmetry, and there's nothing else for you to do because it's already assumed by the code that what you want is zero flux to that phase, and it will complete that phase. But if you say that it's an inlet, then you need to tell it what's the inlet. So that's where CodeSet will come into place. You need to put there how much is the inlet, or how much is the temperature, how much is the flux. So an example here is in CSU boundary conditions, user boundary conditions. What you did previously in the previous tutorial on the interface was to select a criteria that will go and match the name that has on the mesh, that zone or those faces have on the mesh. So the mesh generator can create names for the boundary group of faces and put all of them the same name. If you know that name, you can use that as a selection criteria. So when you were selecting wall R1 or wall R2, the previous tutorial, those names were given by the mesh generator. The person that did the mesh generator put those names, and then you can use that to select them. But you can also use geometrical quantities. You can say X, Y, Z, or you can use tools like box or cylinder or plane to find boundary faces that are in a given part of the domain where you want to put that boundary. So in this example, we get a face that has been named as 2 in the mesh generator, and also where X is less than 0.01, for example. And that function, get FBR, returns the number of faces that it found, so this LT, and an array with those faces, the actual number of those faces, the internal number of the code. And the only thing that you need to do is loop on all those faces and assign the boundary conditions. You loop from 1 to the number of faces, which is this one, that the code found with this criteria. Then you find the actual number of the face by using this instruction. So it goes to this array, and for that number that you're looping on, it's going to give you the real actual numbering of the face. And you assign the type, in this case inlet, and then because it's an inlet, you need to assign the value for that for the 3 velocities here. You have 1.1 for all of them, for example. Similarly, if you wanted to get an outlet boundary condition, and the mesh generator called the faces outlet. Just use the select criteria. And in this case, you only need to put the type of outlet, and the code will automatically set the values for all the variables. Now, the boundary conditions are a bit special, have a bit special treatment in CodeSet, in the sense that it gets translated into what we call coefficients. So imagine that this is any type of cell where you have the cell center I, the face center F, and I prime is the projection of I into the normal of F. So you have the normal of the face here, and because it doesn't have to be hexas, completely orthogonal hexas, it could be anything, then the projection of I into the I prime is the one that is going to help us find the boundary condition here. And that is translated into what you would see is A and B coefficients. So any boundary condition can be written like this. For any face F, you can write A plus B multiplied by the value at the I prime location. So in the case if you had a Dirichlet boundary condition that you say for that boundary face I want to put 10, then basically you just put A equals to 10 and B equals to 0. Okay? If you wanted to have a flux condition, that is FDN equals 20, then you would do this. You would say that is discretized like FD minus F at I prime divided by the distance. So that means that this is, in this case, 20 divided by the distance. So you need to put 20 as this, A as 20 times the distance, and B equals to 1. You don't have to do that yourself as a user. That's what the code does behind it. But what you will find is that when you want to find out what boundary condition has been set up by the code will give you these coef A's and coef B. You have to remember that that's the way to get the boundary conditions back from the code. So there are a few post-processing subroutines that will help you to do this. Okay, so you can see an example of how to calculate thermal flux and boundary temperature by using these functions that are already written for you. So before we had these functions, we'll have to go and program this in reverse, basically, using coef A and coef B, and then find out what the F needs to be. Okay, whereas now you can use this, you can just call all the wall faces and say, please can I have the flux and temperature at that face? And then do whatever you want with this. You can calculate nozzle number, for example. Now, I mentioned before the ghost cells. This comes from the partition of the domain, either for parallel runs or when you have a periodic boundary condition. Imagine that you have these 8 cells in your domain, and you're splitting this into 2 to run in parallel. And the way that Saturn creates that is by adding ghost cells on each one of the tasks, NPI tasks, and synchronizing those ghost cells at the beginning of each time step. Okay? So in a time step, on iteration, this NPI task will only solve this domain, but it will require to know the fluxes through this phase, and to know these fluxes, you need to know the value of this cell, here, the neighboring cell. So it uses the previously saved values here and solve for this domain. Similarly, the other NPI task is solving the domain in parallel, and at the end they get again synchronized. When you do periodicity, it's very similar. You create these ghost cells here that will basically pass from one side to the other of the two periodic boundary condition, ensuring that what goes out is what comes in. Okay? So that's the difference between N cell, which would be, in this case, would be 4, and cell would be 6. So, as I said before, we use MPI. So all of your normal MPI codes have been included in Saturn using specific wrappers. So for ease of use, basically. So it's run already. The user doesn't have to do anything, except in the case that you want to compute something yourself. So for example, if you want to compute the minimum value of something or the maximum value of the temperature, you need to remember that you're going to be running in parallel, and you need to call these parallel functions that will compute first your local maximum and then compare to all the other values of the other computers and find which one is the real maximum in the whole domain. Okay? There's a lot of examples of these parallel calls in CS user exit operations. Some other considerations in C. As I said before, we're slowly moving towards having most of the code in C. Here are some of the main subroutines that are already in C. And you will find that sometimes you need to do everything in C rather than being able to do it in Fortran, because we move a lot of things for the C part. Here are some of the examples more important. You have user coupling, where you can couple with codes or with Saturn itself. You can set the parameters, the same thing than was done in Fortran. You can modify the mesh with something that we will see later. And you can tune the performance by choosing different parameters to optimize the runs on the machine that you're using. And some others are post processing the solver and the machine. Similar to Fortran, the subroutine starts with a description of what the subroutine is and license. And then you have the includes, so the headers normally, with the standard C libraries and the local ones. And then you have your definition of the functions, like in your normal C program. And then you will basically continue with your function, whatever you want to do. There's a command called bft alloc to allocate the memory, and bft free. And you'll find that bft printf is analog to printf the same way. It's the wrapper that is done inside CodeSet to make sure that it works in different compilers and different machines. You also have some types that define CodeSet, so real 2T would be a vector of two real values, for example. And you also have macros that particular to CodeSet, like these apps, the absolute value. This helps you again when sometimes you have different macros for different compilers, and this will wrap it for you. So regardless of what you do, you will be able to use that. So this is the Doxygen example. So you can see, I'm going to try to get it here. Try to share my screen. No, can't share my screen. Yes, can. All right. So this is the CodeSet website. And if you go to documentation, in this case, you have FAQ, you have the tutorials, the best practice guidelines, and each version has its own documentation page. So you'll see here online documentation. This is documentation. This is something that is created semi-automatically, and you have a copy of the PDFs for the user guidance, theory guidance. So if you go here, you see that you have a main menu here on the left, okay, and then you have some explanations on how to do things that we've gone through already, and here you have variables and structure reference. And here it tells you how to access and manage mesh entities, for example, or variables properties using the CS field API. Okay, so this is what I was telling you before, that you have CodeSet will use this function to call for in variables. And at the bottom, you have all the list of how to get things. So how to get the pressure, the velocity, and to do anticipation, for example, you would use this on C or the other one in Fortran. Okay. Similarly, with the properties, you have the way to get all the properties. And for each of the specific modules, as well, you have details. And the good thing about the Doxygen documentation is that you can look at anything that you want. So you click on this field, it's going to tell you what the function is. You have all of them here, all of the functions, subroutines that make the code are there. Okay. You have also, if I go here, the user examples, you have a copy here. So if you, for example, go to other one, pre-processing mesh modifications. Here is the examples that you have. How to change the coordinates, for example, go from, in this case, go from 1 to 1000, so meters, or how to extrude part of the mesh, how to tag cells, and another useful tool is boundary layer insertion, which basically you create a boundary layer refinement in the walls. It can be done automatically with Saturn. That's an example. Mesh refinement, in which the cells are split equally. Okay. And how to read and modify the mesh. Example, you can transform the mesh, you can rotate it, you can translate it, you can do some smoothing, you can find the bad cells, for example, you can join different meshes, and you would put the periodicity. Okay, so there's a lot of information here. Stop. So, any questions so far? See what's in chat.
Okay, if there are no questions, if we go for the next tutorial, I mean, there's a part on Archer 2, and it would be good to for all of you to log on Archer 2 and to actually configure your account. Could you do that? So when you go to Archer 2, basically, before Juan start to explain what the tutorial is about, so please, that's on Archer 2, that's not on the local machine, okay? So you have to be on Archer 2. And what you need to do is that you need to type this line first, and then this one. This should configure your account, okay? And when you're done with that, when you type this, when you type Saturn any GNU, it should return that line, okay?
So I put it here. Oh, you should. It should look like this. Okay. Obviously, with your username, but that's what it should be.
And Juan, if you type ls, you should have a directory work in there, hopefully. Okay.
Forget about it.
Oh, and if you type ls-mtr, you should have work pointing on the slash work folder. Yep. Good.
You probably don't have all of that stuff, just that last line.
Yeah. The last line corresponds to a symbolic link to the workspace, and that's in the workspace that you are going to submit a simulation from. Could you let us know how it goes? Are you experiencing problems?
Feel free to turn your mic on, your camera on. Well.
Yeah. Note that you will have to do that only once. Next time you log on, actually these settings will be ready for you.
And if you type this, you should get this.
Yeah.
Right? Type CodeSet, the same as when you're typing on virtual machine. So, is there someone that doesn't get this working? No. 1, 2, 3, 4, 5.
So for people it works. I mean, they can start the tutorial, I think. So the first part is is basically an extension of the previous tutorial. And this time, simulation is going to be 3-dimensional, so a much bigger mesh, which have around 2 million, compared to the few hundred cells he had before. And this mesh is going to include also the solid, and the flow is going to go around basically the center cylinder and account for the conjugated transfer. So the setup is on the virtual machine first, and then when the setup is finished, you will need to copy some files across on the Archer 2 and submit this, a simulation through a queuing system for a simulation which is going to run overnight. Yeah.
Yeah. One thing I would say, in addition to Chelsea's, this is the mesh that he was talking about, it's important that you follow the instructions as to create your case in a local machine and then create the case again in the remote machine, because as you saw in the CodeSet, the installation paths are different, so you cannot just copy the whole study across and expect that to work. When you create the case, it copies paths and locations of files that are specific to each machine. Okay. And another thing that it's part of this tutorial is to use a subroutine, which is explained here in section 4.3. To edit the subroutine, you can use any editor that you prefer. You can use VI, you can use Emacs, you can use Kate, anything that you have in the machine to work. Another possibility is also to use the editor in CodeSet, which I'm going to show you. So when you open the graphical interface, here at the top you have these buttons that manage files with data, manage user functions within the SRC folder, test compilation of the user functions, or view output for a log file of a run. So if you click on manage, another window appears, and you'll see that you have your reference folder and examples folder. You can look at these subroutines by double clicking on it. gonna appear on the left. And if you want to use them, you need to copy to the SRC folder and then edit that one in the SRC folder. Okay. If you edit these ones in the reference or the example, they're not going to be used. To copy them here at the top and then edit that one. Okay. Promise that this is very simple editor. It's a bit, doesn't have many features, so you don't kind of search and replace and things like that. It's basic. So if you can, if you prefer to use any other thing, that's fine. Okay. The important thing is that you can also test the compilation here. Okay, and if it's successful, it will tell you that it's successful. And you can see the details of which is the details is just the compiled log file.